layer thicknesses, selection of layer thicknesses. So for this we will first calculate the structure number, that is SN1, SN2 and SN3. If there are 3 layers, then we will find SN3. If there are 2 layers only, then we will find SN1 and SN2. So this SN1 and SN2 can be found from equation. We have already equation, I will show you later. Once we find this SN1 and SN2 from equation, then we will be able to find the thickness of asphalt layer D1 and the thickness of granular base. So by writing the SN1 value here, and A1 is the constant, for the asphalt layer it is 0.42, then we will find the D1 by putting this D1 value here and A1, and also calculating SN2 from the equation. Again A2 and M2 are constant, then we can calculate the thickness D2. So let me show you the equation in which SN1 is present, from where we can find SN1. Page number 523. This is the equation. In this equation, W18 is the easels. By taking log of this value, it is the left hand side, and it is the right hand side. In right hand side we have these values: ZR, S0, standard deviation, ZR is the constant, Sn is the structure number here, and del PSI is the change in the present serviceability index, and Sn is the structure number, and Mr is the resilient modulus of the layer, for which layer you are going to calculate the SN1. If you are going to calculate SN1, then the resilient modulus taken will be from the second layer. Similarly, if you are going to calculate the structure number for the second layer, then you will use the resilient modulus of the third layer. So writing this equation in Excel, here is the easels 10 power 4, and it is the left hand side of the equation, that is log of easels. So log of easel is equal to 4. Just look at the equation here, log of easel, the left hand side. The right hand side I write in Excel is in this cell. Here I put the values for different parameters like D5. So ZR value is this, multiplied by B5. B5 is this S0 value. ZR multiply S0 plus 9.36 into log of Sn plus 1. So look at in the equation, ZR plus 9.36 into log of Sn plus 1, and then minus 0.2 plus here minus 0.2 plus log of B6 del PSI value 2.1 divided by this whole term divided by 0.4 plus 1094 divided by B14 plus 1. So B14 is actually the structure number. I also put this B14, the structure number here, this value. So putting this and taking the power 5.19, closing the bracket, and then add 2.32 into log of B8, the resilient modulus. Now look here, I put the resilient modulus, the modulus of stiffness of the second layer, if we calculate the thickness of first layer. Similarly, if we calculate the thickness of second layer, we will use the resilient modulus of the third layer, like here resilient modulus this. So by putting here the Sn value and the modulus of stiffness value here, minus 0.87, we got 4.0055. Just by changing the SN1 value, this value get changed. Like here it is now 0.85. If we just make it 0.4, the value got changed. So 2.87 is smaller than this left hand side of the equation. So by in order to make it equal, we will just change this value until the left hand side becomes equal to right hand side. This is less, so we will increase this structure number from 0.4 to 0.7. It becomes 3.6. Now again increasing this 0.7 0.85. If we make it 0.85, then it will become 4.00. So now the left hand side and right hand side both are equal, so the structure number value calculated is 0.85. Similarly, for the structure number 2, we will make the left and right side of the equation equal. So here it is 4 and there here it is 4.06. Just watch. Again I put all the values the same. Snot constant, ZR constant, PSI constant, del PSI, and now the MR value get changed. For this, for the second layer, the third layer, resilient modulus will be used, that is subgrade resilient modulus. And by using this and also using the structure number this, we calculated the value this. So this one, so clicking enter, this is equal to 4.06, and this is, so it means that these values are similar, are equal. So by changing this value from 1.05 to 0.7, the value got decreases, so it's not equal. Again we will move above, that is 1.2. so now it is higher than 4, so we will reduce, so 1.05, then now it become equal. So it means that the structure number is 2. Structure number 2 is 1.05. so we find out the SN1, SN2. Now we will find out D1 and D2. Now look at the book here. This is D1. So for D1, SN1, we calculate this, and A1 for the asphalt layer is constant. That is A1 is 0.42 and A2 is 0.14. So here D1 is equal to SN1 divided by A1. So dividing these two values, multiply it with 2.54. Convert this into centimeter. Dividing the structure number SN1 by A1, we will get answer in inches. So converting it to centimeter, we multiply it with 2.54, so we got a value of 5.1 centimeter for the D1. Similarly for 4.4, for the D2, we use the formula here. D2 is equal to SN2 minus A1 D1. Here look at this, if we just move this A1 to the left side, then SN1 is actually equal to A1 D1. So we can also write here SN1. So by dividing the SN2 minus SN1 by A2 M2, we got D2. So here in the Excel sheet, this is the SN2, this minus this, this minus this, multiplied by G7 is actually G7 is this value, M1 value, multiplied by 2.54 and then divided by 0.14 A2 value. We got 4.4 centimeter D2. So now we have thicknesses for the asphalt layer and for the granular base. So using these values in cost, now for cost, the 26.5 is the asphalt rate cost. I mean that $26.5 per cubic meter, and then B16 is actually the thickness in centimeter here. So converting this value into meter, multiplying it with 10 power minus 2, then it become in meter. So it is the rate, it is the thickness up to this point, and then multiply 3.65 meter is the lane width for single lane, and 1000 is the 1 kilometer distance. So this is the cost of the asphalt layer, and plus this is the cost of granular base. For granular base, B17 thickness of base multiplied by 10 power minus 2, converting it to meter, and then multiply it with 1000 meter and multiplying with the width of 3.65 meter for single lane, and then multiply it with 13.5 the granular base rate, $13.5 per cubic meter. So pressing enter, we got $7,118. Similarly, So one thing here is this MR value is 140 megapascal. Converting it into PSI, we multiply it with 145.038, so we get 2305 PSI. And this is the E2, the granular base, whose modulus of stiffness is 200 megapascal. Converting again it to PSI, we get 29008. And similarly the modulus of stiffness 4000 megapascal, converting to PSI, we get 580,152. So this is the case for the natural soil. Now if we just make the soil stabilized with cement, then the MR value will change. Look at this value. This value is 2305 and this value is 28,000. It means that the resilient modulus increases by using the cement in order to make the soil stabilized. So by increasing this value, again using the ESALs 10 power 4, the left hand side, I make the left hand side and right hand side equal for the same ESALs, just changing the MR value. The thickness is got changes, 5.1 centimeter and 0.8 centimeter. This is the asphalt thickness, this is the granular base thickness, and then using these thicknesses we calculate the cost. Now look at the cost here. The cost is 7,000, almost 7,000 plus, and here 5,000 plus. So it means that by using the cement stabilized soil, the cost of the road decreases almost $2,000. Now we check these values for ESALs of 10 power 4. If we just go to check for the ESAL 10 power 5, this is for 10 power 5, just changing this value and this value to 10 power 5 from 10 power 4. Other things are same. Similarly, these values for the natural soil 10 power 6, and then it is 10 power 6, and then 10 power 7, 10 power 7. So this is the natural and cement stabilized soil cost comparison. Now it's time using plastic stabilization, clay with the plastic stabilization. So here for using 1% PE and changing the ESALs from 10 power 4 to 10 power 5 to 10 power 6 and to 10 power 7, we got different values of thickness. Here 5.14 and 4.4, here 8.5 and 3, and here 12.7, 4.8, 18.1, 4.5. So these are actually the thicknesses which we calculate from the different resilient modulus. Here if we see, the resilient modulus for every 1% is constant. Here 21,060, 21,060, 21,060 and 21,060. The only value changing is ESALs is 10 power 4, 10 power 5, 10 power 6 and 10 power 7. After this we are moving toward the plastic having percentage 2%. So for 2% and using different ESALs like 10 power 4, 10 power 5, 10 power 6, 10 power 7, we calculate the thicknesses, and based on these thicknesses we again calculate these costs. For these thicknesses this cost, for these thicknesses this cost. So these values of cost, this and the other above two values, this one and this one, is for 1% with changing of ESALs from 10 power 4 to 10 power 7. The same thing is done for PE percentage of 3 and PE percentage of 3, PE percentage of 3, PE percentage of 3 with changing of ESAL 10 power 4, 10 power 5, 10 power 6, 10 power 7. And you know that here the ESALs value are changing as well as the resilient modulus value for different percentage also changes. Like here for 3% PE the resilient modulus is 21,466, but for 2% it is 21,451. Because if you are going to increase the percentage of PE, the resilient modulus increases from 21,451 to 21,466, and by increasing the 3% to 4%, the MR value again increasing from 21,466 to 24,801. Thus the thickness is further reduces. and the cost also reduces. So these four tables are for 4% with different ESALs values. This table is for 10 power 4 ESAL, this table is 10 power 5, and this for 10 power 6, and this for 10 power 7. So there are 4 tables for each kind of soil, and here is a graph which compares the cost of different kind of soil. So the natural soil, the blue color, is on the top. It means that the cost for different ESALs is on the top is high comparable to other kind of soil. Like if we just change the resilient modulus of the other kind of soil, the cost decreases. If we see for the cement treated, the last one, lower one, is actually for the cement treated in orange color, and its cost is comparable to the natural soil, using natural soil for subgrade. And then this is the value for 1%, 2%, 3%, and 4%. This line is for the natural subgrade, and these values for the 1%, 2%, 3%, and 4% plastic, using 4% plastic. So these values is decreasing. It means that the cost of the soil stabilized with plastic is small to that of natural soil, and the soil stabilized with cement is further less than the cost of the road with a subgrade stabilized with plastic and natural soil subgrade. So this is all the work which I have done. Okay brother, if any confusion, then ask me.